Toothpaste is one of the most ordinary products in daily life. It sits quietly on bathroom sinks across the world, used almost automatically every morning and night. Few people pause to wonder how it is made, where its ingredients come from, or how much science and engineering stand behind that familiar minty foam. Yet the journey of toothpaste, from raw materials to finished tube, is far more complex than most imagine. Among the most surprising chapters in toothpaste history is the traditional use of animal bones as a key ingredient. While this practice may sound unusual or even unsettling today, it was once a practical and scientifically sound solution for creating effective dental abrasives. Understanding this process offers a fascinating window into industrial chemistry, historical manufacturing methods, and the evolution of consumer safety standards. This article takes you step by step inside the toothpaste factory, tracing the complete production process using animal bones, from their origin as slaughterhouse byproducts to their transformation into a refined, safe, and effective toothpaste component. The role of abrasives in toothpaste. Before exploring bones specifically, it's important to understand why abrasives are essential in toothpaste. Toothpaste does not clean teeth through chemicals alone. Its primary cleaning action comes from mild abrasives that remove plaque buildup, polish tooth surfaces, dislodge food particles, and help prevent stains. The challenge is balance. Abrasives must be strong enough to clean effectively, but gentle enough not to damage tooth enamel. Calcium-based compounds have long met this requirement, making them ideal candidates for toothpaste formulations. Animal bones, rich in calcium phosphate, became one of the earliest reliable sources of such abrasives. In traditional toothpaste production, bones were sourced as byproducts from slaughterhouses, primarily cattle bones. These bones were readily available in large quantities due to the meat and food processing industries. Rather than being discarded as waste, they were repurposed for industrial use. Cattle bones were preferred because they contain high concentrations of calcium, phosphates, and mineral compounds compatible with human teeth. This practice reflected early industrial efficiency, using every part of an animal for useful purposes. Transportation and storage. Once collected, bones were transported to processing facilities. At this stage, they were still raw and contained organic matter, fats, and moisture. Proper handling was crucial to prevent decomposition, odors, and contamination. Bones were typically stored in ventilated areas and processed as quickly as possible to maintain quality. The first major processing stage was thorough cleaning. Raw bones carried blood residues, fat and grease, remaining meat and connective tissue. These substances had to be removed completely to prevent bacterial growth and unpleasant odors. Industrial washing. Bones were washed using large volumes of water, often in rotating drums or conveyor-based washing systems. High-pressure sprays helped remove stubborn debris, while water temperature was carefully controlled to avoid cooking fats into the bone surface. This step laid the foundation for all subsequent processing stages. Incomplete cleaning would compromise the entire batch. Even after washing, bones still contained fats trapped within their porous structure. These fats posed serious problems. They interfered with high-temperature processing, they caused odors, and they reduced the purity of the final product. Degreasing was therefore essential. Boiling and steam treatment. Bones were boiled in large vats or exposed to pressurized steam. This process melted residual fats, allowed oils to separate and drain away, and further sterilized the material. The extracted fats were often collected and repurposed for other industries, such as soap or lubricant production. After degreasing, bones still contained significant moisture. Drying was required before high-temperature treatment could occur. Industrial drying ovens. Bones were placed in large industrial drying ovens where warm air circulated continuously. This step prevented steam explosions during calcination, improved energy efficiency in kilns, and ensured uniform heat treatment. Proper drying also reduced microbial risks and stabilized the material for storage. Calcination was the most critical and transformative stage. Dried bones were placed in kilns or furnaces and heated to temperatures ranging from 600 degrees Celsius to 1000 degrees Celsius. What happens during calcination? At these extreme temperatures, all organic material was completely burned away. The bones were fully sterilized, carbon compounds were removed, and the remaining structure transformed into bone ash. The result was a white, brittle substance composed mainly of calcium phosphate. Safety and control. Temperature control was vital. Too low and organic material remained. Too high and the mineral structure could degrade. Skilled technicians monitored kiln conditions continuously. Bone ash, though sterile and mineral-rich, was not usable in its raw form. It had to be converted into an ultra-fine powder suitable for toothpaste. Industrial milling equipment. The ash was processed through ball mills, roller mills, and high-speed grinders. These machines reduced the material to microscopic particle sizes. Why particle size matters? If particles were too large, they could scratch enamel, irritate gums. If too fine, they might lose cleaning effectiveness. Precision was essential. After grinding, the powder was passed through fine sieves to remove oversized particles, impurities, and inconsistencies. Only powder with uniform particle size advanced to the next step. Additional purification. In some facilities, chemical purification steps removed trace metals or unwanted minerals, further improving safety and quality. Before being approved for toothpaste use, bone-derived powder underwent rigorous testing. Laboratories examined purity levels, particle size distribution, chemical composition, absence of pathogens and contaminants, and compliance with standards. Only batches meeting strict industry and regulatory standards were approved. Any deviation resulted in rejection or reprocessing. The approved bone-derived powder was blended with other essential toothpaste components, including fluoride compounds for cavity prevention, humectants like glycerin or sorbitol to retain moisture, binders to control thickness and texture, flavoring agents for taste, and preservatives for shelf stability. Controlled mixing. Large stainless steel mixing tanks operated under controlled temperatures, vacuum conditions to remove air bubbles, and precise timing. This ensured consistency and product stability. Homogenization ensured all ingredients were evenly distributed. This prevented separation and created the smooth, uniform texture consumers expect. The toothpaste became creamy, stable, and consistent from first squeeze to last. Finished toothpaste was pumped into collapsible tubes using automated filling machines. Tubes were precisely measured, heat-sealed, and coated with batch numbers for traceability. Final packaging. Tubes were boxed, palletized, and prepared for distribution to retailers worldwide. From bones to modern alternatives. Today, most toothpaste manufacturers have replaced bone-derived abrasives with synthetic or mineral alternatives, such as hydrated silica, calcium carbonate, or synthetic hydroxyapatite. These materials offer similar benefits with greater consistency and broader consumer acceptance. However, the historical use of animal bones played a vital role in shaping modern dental care. Conclusion: a hidden story behind a Bailey habit. The journey from animal bones to toothpaste highlights the ingenuity of early industrial manufacturing and the scientific principles that continue to guide product development today. What once began as a practical reuse of byproducts evolved into a carefully controlled, safety-driven process that laid the foundation for modern oral care. Every time toothpaste is squeezed onto a toothbrush, it carries with it centuries of experimentation, chemistry, and engineering. Proof that even the most ordinary products have extraordinary stories behind them.